Welcome to the zeroth dimension. You are a point. No length, no width, no height, just a location in space, defined by a single coordinate. In mathematics, that is exactly what a zero-dimensional object is, something that has position but no size. From a geometric standpoint, a point contains no measurable distance. You cannot move because movement requires at least one direction. In zero dimensions, there is nowhere to go. It is pure existence without extension. In physics, we sometimes approximate particles as points, meaning they have no internal structure at the scale we are measuring. It is a useful abstraction, even if reality is more complicated. If you line up an infinite number of points, each one distinct, you begin to build something new. You create length. Stack those points side by side and you get a line. Now we are in one dimension. You have length, but still no width or height. In one dimension, you can move forward or backward, nothing else. If two beings lived here, they could not pass each other without overlapping. Their entire universe would be a straight path extending infinitely in two directions. Mathematically, this is the real number line. Every position can be described with a single number. In physics, one-dimensional systems are simplified models. A vibrating string, for example, is often treated as one-dimensional because its motion is primarily along its length. But perception in one dimension would be strange. If you looked at another object, you would only ever see a point. You could not see its full extent because you have no width to step aside and look from an angle. Perspective does not exist. Add another independent direction perpendicular to the first, and everything changes. Pull the line sideways and sweep it through space. Now you have a plane. Two dimensions, length and width. In two dimensions, shapes exist. Triangles, squares, circles. You can move forward and backward, left and right, but there is still no up or down. A classic thought experiment comes from Edwin Abbott's Flatland, a story about creatures confined to a plane. If a three-dimensional sphere passed through their world, they would not see a sphere. They would see a circle that appears, grows, shrinks, and vanishes. To them, it would look miraculous. Biology in two dimensions presents real problems. A digestive tract that runs straight through the body would split it into two separate pieces. Circulation would be difficult. Many of the structures we take for granted in three dimensions depend on depth. From a mathematical standpoint, two-dimensional space can be described by pairs of numbers, x and y. Surfaces in physics are often treated as two-dimensional, like the surface of a pond or a sheet of graphene. But our lived experience adds one more axis. Stack planes on top of each other and you form a volume. Welcome to three-dimensional space. Now you have length, width, and height. Cubes, spheres, mountains, oceans. This is the space we inhabit. Every location can be described with three coordinates. Interestingly, even though we live in three dimensions, our eyes detect a two-dimensional image. The retina is a flat surface. Your brain reconstructs depth using shadows, motion, and differences between the images in each eye. Depth perception is an interpretation, not a direct measurement. In physics, three spatial dimensions appear to be fundamental. Every experiment so far confirms that space behaves as three-dimensional at the scales we can test. Gravity, electromagnetism, and the other forces operate within this three-dimensional framework. But space is not the whole story. There is another dimension we constantly move through. In modern physics, the fourth dimension is time. Space and time are woven together into what we call spacetime, described by Albert Einstein's theory of relativity. In this framework, an event is not just where something happens, but when. A complete description requires four coordinates, three for space and one for time. Mathematically, you can imagine a four-dimensional object as a three-dimensional object extended along a new axis. If you think of your life from birth to death, relativity treats it as a world line stretching through space-time. You are not just a three-dimensional object moving through time. You are a four-dimensional object extended across it. This idea has real physical consequences. Time slows down for objects moving near the speed of light. Gravity curves space-time, and that curvature guides the motion of planets and light. GPS satellites have to account for these relativistic effects, or your phone's location would drift by miles each day. The fourth dimension is not science fiction. It is built into the equations that describe the universe. But what about dimensions beyond four? Here we move from confirmed physics into theoretical territory. In some interpretations of quantum mechanics, especially the many worlds interpretation proposed by Hugh Everett, every quantum event can branch into multiple outcomes. The idea of a fifth dimension is sometimes used as a visualization tool for this branching structure. In this picture, the fifth dimension represents different possible timelines that arise from the same initial conditions. All versions share the same laws of physics, the same fundamental constants, but differ in outcomes. It is important to be clear. This branching multiverse is a hypothesis. It emerges naturally from the mathematics of quantum mechanics, but we do not have direct experimental proof that all branches physically exist. Still, as a conceptual model, you can imagine a plane of possibilities where every choice creates a new path. The fifth dimension becomes a way to describe the space of alternative histories. Take that entire collection of possible timelines and imagine being able to move between them without retracing every step. The sixth dimension is often described, in speculative models, as the space of all possible timelines that share the same physical laws but allow direct connections between them. Again, this is not established physics. It is a geometric way of visualizing higher-order possibilities. In theoretical models such as string theory, extraspatial dimensions are proposed beyond the familiar three. However, these additional dimensions are not large and accessible like in science fiction. They are thought to be compactified, curled up at incredibly small scales, far smaller than an atom. The sixth dimension, in popular explanations, becomes a way to imagine shortcuts across the landscape of possibilities. In rigorous physics, extra dimensions are mathematical degrees of freedom required to make certain equations consistent. Now, we change something deeper. Instead of varying outcomes within one set of physical laws, imagine universes with different initial conditions or even different constants of nature. In some cosmological models, such as eternal inflation, our observable universe may be just one bubble in a vast cosmic foam. Each bubble could, in principle, have different values for fundamental constants, like the strength of gravity or the mass of elementary particles. The seventh dimension is sometimes described as the set of all universes with different starting conditions. In more formal terms, it resembles the landscape of possible vacuum states in string theory. Most of these hypothetical universes might be lifeless or unstable. A slight change in the strength of the strong nuclear force, for example, could prevent atoms from forming. The range of life-friendly parameters appears narrow, at least as far as we understand. If the seventh dimension is like a line connecting universes with different physical constants, the eighth dimension is often imagined as a plane of all such universes. Here, you are not just moving between different histories of one universe, you are moving between entirely different rulebooks. In string theory, the number of possible vacuum solutions is enormous, sometimes estimated as 10 to the 500 or more. Each solution corresponds to a different way extra dimensions could be compactified, leading to different particle properties. These ideas are mathematically rich, but experimentally unverified. We have not detected extra compactified dimensions. Particle accelerators like the Large Hadron Collider have not yet revealed clear evidence of them. Still, higher dimensional models remain serious candidates for unifying gravity with quantum mechanics. The ninth dimension, in popular frameworks, represents a way to navigate across the full range of these universes more freely, as if folding the entire structure to create shortcuts. In mathematics, when we speak of 9 dimensions, we simply mean a space described by 9 independent coordinates. There is nothing mystical about it. Higher dimensional spaces are common in advanced physics. Phase space, which describes all possible positions and momenta of particles, can have dozens or millions of dimensions. The challenge is not defining higher dimensions. It is determining whether any of them correspond to physical directions we can access. At present, no experiment has demonstrated that large extended spatial dimensions beyond 3 exist. If extra dimensions are real, they are likely compactified at scales far smaller than we can directly observe. In certain versions of string theory, the mathematics requires 10 space-time dimensions, 9 of space and 1 of time, for consistency. In M-theory, that number becomes 11. These additional dimensions are not vast realms we can travel through. They are tightly curled up, possibly at scales around 10 to the minus 35 meters, the Planck length. When popular explanations describe the 10th dimension as containing all possibilities, all timelines, and all physical laws in a single structure, They are blending physics with philosophical speculation. What is accurate is that some candidate theories of everything require extra dimensions to unify all known forces. The 10th dimension, in this context, marks the limit of certain mathematical frameworks. Beyond it, the equations break down or require new structures. At the deepest level, higher dimensions are tools. They allow physicists to write equations that unify gravity with quantum mechanics, to describe particles as vibrating strings, or to explore the geometry of spacetime itself. Whether these dimensions are physically real in the way length and width are real remains an open question. And here's the quiet twist. In pure mathematics, a point in 10 dimensions is still just a point. It is defined by 10 numbers instead of 1. In that sense, the zeroth and the highest dimensions share something in common. They are both descriptions of structure, not places you can stand. If you found this journey through dimensions helpful, give it a like and subscribe for more explorations of the universe. There is a lot more structure hiding in reality than meets the eye.